Thank you. Now I welcome Miss Divya to welcome the gathering. Divya, Miss.
Okay, thank you.
Yes, Divya, you can have the
Okay.
yeah.
Good morning, all. First of all, I would like to give special thanks to the organizers of this webinar, especially my research guide Anjali Miss, for giving me an opportunity to introduce such an eminent personality. Let me introduce Dr. Narayanan Sir, Assistant Professor, Indian Institute of Technology, Madras. He secured his bachelor degree in mathematics from University of Calicut, MSc Operations Research and Computer Applications from Cochin University of Science and Technology, and PhD from the Institute of Mathematical Sciences, Homi Bhabha National Institute. His areas of research interest are graph coloring, extremal graph theory, extremal combinatorics, graph algorithms, and graph domination. He worked as Junior Research Fellow in Tata Institute of Fundamental Research, Mumbai. Visitor at University of Silona Gora, Poland. Research Scholar at IMSC, Chennai. Postdoctoral Fellow at Indian Institute of Science, Bangalore. Assistant Professor at CRAU Advanced Institute for Mathematics, Statistics and Computer Science, Hyderabad. Postdoctoral Fellow at National Taiwan University and also at France. From 2012 onwards, he is working as Assistant Professor at IIT Madras. He was the Organizing Secretary of 4th India-Taiwan Conference on Discrete Mathematics. He has more than 18 journal publications and more than 6 conference publications. On behalf of everyone present here, I invite Dr. Narayanan Sir to handle the session. I also welcome HOD, Swarnamis, and all other faculty and also all participants to this webinar. Thank you.
So we can start the session, right?
Oh, okay. Thank you. One second, let me see. Is it visible now?
Yes, sir. Yes, sir. It's coming. It's coming.
Yes, sir.
So can I start?
Yes, sir, of course.
Okay. If there is any issue, like just let me know. Any questions? This is a very kind of very recent result proved last year only by Yaroslav Shitov, and so the heterogeneous conjecture is like around 50 plus years old, and we are going to see a disproof of the same by construction of a counterexample. So this paper appeared in the Annals of Mathematics, and it's a very short paper actually. If you feel like it's just 1.5 pages, but if you try to read it, it's a little difficult to follow, because the language used is very cryptic, and he has put together lots of things into this 1.5 pages. So unless you are very familiar with the literature, it's kind of difficult to understand what is written in this thing. So when I took a first look at this, I gave it up on this thing because it was very difficult to follow. Then I was fortunate to attend a lecture by Suding Su when I visited China, and he was planning to give a talk on this to some audience, and he prepared this and then told that he will give a talk to us. And so my lecture is based on the lecture I attended of Professor Suding Su, and and he did a an excellent job of presenting this. So all these points are kind of clear. So now I am going to present this result, and if you have any questions in between, please feel free to stop me and ask. Okay. So here is an outline of the talk. So we will look at what is Head-Archimedes conjecture. Then about exponential graphs. That is that is a well-studied class of graphs within the framework of Head-Archimedes conjecture earlier. And then we look at the result of Paul and Roche. It's a very old result, 1946 or something, which is also very well known. Okay. Now, then we show some way to increase the chromatic number of the graph to be larger than some number, and then we get a counterexample by showing that there is no coloring for the product of graph with the exponential graph with C colors. Okay, so this is the idea of the proof. Now we use a smart way of counting to basically show that there is no C coloring for the exponential graph. So the main objects in our study are going to be a graph G, which we will construct using a result of Roche, and the exponential graph of the graph G, which we will see in a minute, and their product. Okay, so these are the three type of graphs that we are going to look at. Okay, so we start with the assumption that we are looking at finite simple graphs G and H. Okay, but of course, in the meantime, in between, we will come with some other graphs with the loops, but we will mention it at that time. So G and H are finite simple graphs. Then the chromatic number of the graph G is defined to be the minimum number of colors such that you can color the vertices or map the vertices to these colors, so that adjacent vertices get different colors. Right? This is well-known definition of chromatic number. And then you have the direct product of two graphs. This is also well known. So the direct product of the graph is defined on the Cartesian product of the vertices of G and H, V of G cross V of H. And then you have two vertices, let's say GH and G dash H dash in the product graph is adjacent if and only if G is adjacent to G dash and H is adjacent to H dash in the graph H. Okay, so this is the direct product. So we have the finite simple graph G and H. You have the direct product. Now, here is an example of the direct product. So you have the path on 4 vertices P4 and cycle on 3 vertices C3. So you take the product of these two, you are going to get a graph like this, what you can see. So if you look at the definition, you can see that if you take one edge as a graph G and one edge as the graph H, then the product graph is a disconnected graph with two edges, which looks like this, right? Like if you look at the Cartesian plane, then the edge will look like a cross, and that is why the symbol for the direct product is usually G cross H. Now, it is kind of easy to see that if you have two graphs G and H, then their direct product can be colored with with the minimum of the chromatic number of G and H. So why is this? Well, if you look at any graph G, right? So you have the G cross H. If you take the graph G, and if G has a coloring using some number of colors, whatever it is, right? So take a coloring of G, and the coloring of G I am going to use to get a coloring of H, of the product. So what I do is that I look at the vertex G comma H in the product, and then without looking at what H is, I am going to give the color of G to this vertex. Okay, so the small g is the color, the vertex in the graph G, and what is the color according to the color given in the proper coloring of G, I am going to give that to G comma H. So G comma H, for every H in the graph H, I am going to give the same color. Now, why is this a proper coloring? Because you can see that in the direct product, two vertices are adjacent if and only if G dash is an H and H dash is an H. Now, because the coloring is proper if if you have GH and G dash H dash, then unless G and G dash are adjacent, they will not be adjacent in the product graph. So for a fixed vertex G, we know that GH and GH dash are going to be always an independent set. So they can all be given the same color. Similarly, if G is adjacent to G dash, we know that phi dash of GH and phi dash of G dash H are going to be different because G and G dash get different colors in the proper coloring of G. Okay, so therefore we can see that from the coloring of G, we can get a coloring of the product. Similarly, from a coloring of H, right, we can get a coloring of the product. So therefore, if I know that chromatic number of G is something and chromatic number of H is something, you take the minimum of these two numbers, I definitely have a coloring of the product graph with the minimum of these two numbers, right? So we know that chromatic number of the product is at most the minimum of chromatic number of G and chromatic number of H. Now, what Heredniemi conjectured by observing several graphs and seeing that this works is that it is actually equal to the minimum. That you don't you cannot have a coloring with less number of colors, right? If G and H are colored with some number of colors, you cannot color the product with less than the minimum of these two. And in the last 50 years or so, there have been so many papers written on this conjecture, and almost all of them were trying to prove that this conjecture is true for certain classes of graphs. And for many classes of graphs, they proved that it is actually true. On the other hand, there were some attempts to disprove it, which was having not much of a progress till last year when Shitov came and showed that there is a counter. And it is very surprising that the actual actual what do you call actual material to present this is very little. That you don't really need too much of heavy graph theory or anything to really understand this proof, but it's very clever. Okay, so but very simple also. So let us see. So is it okay so far? Are you following?
Yes, sir. Yes, sir.
Okay.
Yes, sir.
Okay. So now So what we are going to prove is that there are graph G and H such that their product can be colored with less than the minimum of the chromatic numbers of each graph. So let us look at what is the exponential graph of a graph G. Okay. So let C be a positive integer. Then I define the exponential graph ECG to be, so you look at all possible functions from the vertex set of G to C, or basically it's all possible colorings where I don't restrict the coloring to be proper. Okay, I can give any colors, right? I can give all the vertices the same color also. That is also a good color, right? So I look at all possible colorings of the graph G using C colors. Okay, at most C colors. So we have the set of colors 1 to C, and then I'm going to color all the vertices of the graph G using some colors, right? Now look at all such colorings. So we know that number of colorings is going to be exponential. That is why the exponential graph name. So you look at all possible colorings, and these colorings are the vertices of the new graph, exponential graph. So the set of all possible colorings is the set of all vertices of the exponential graph ECG, and then two colorings or their functions basically, right? And any coloring is a function from the vertex set to 1 to C. So two colorings, let's say phi and psi, they are adjacent if and only if for every pair of adjacent vertices in the graph G. Okay, for every x adjacent to y in the graph G, the vertex x and vertex y should be given different colors by phi and psi. So phi of x is different from psi of y. So two colorings are adjacent if and only if for every adjacent vertices in the graph G, they give distinct colors. Okay. So this is the definition of the exponential graph. Now, so exponential graph ECG contains all possible colorings, both proper and improper, using at most C colors as its vertices. Okay. Now, one easy observation is that phi is adjacent to phi if and only if phi is proper. Right? A coloring is adjacent to itself. So there is a loop in the vertex exponential graph if and only if the coloring is proper. So for every proper coloring, there is a loop at vertex in the exponential graph. So why is this? Because a proper coloring will always give distinct colors to adjacent vertices, right? And and if the coloring is not proper, of course, for some pair of adjacent vertices, they will give the same color, right? That's why it's called not proper, improper. So that tells you that phi is going to be adjacent to phi if phi is proper, because the earlier condition of adjacency is satisfied by phi if it is proper. Now, another even more important observation is that the graph, G direct product with ECG always admits a proper C coloring. So you take any graph G, okay? Any graph G, I don't worry what is the chromatic number of G. It can be anything. It can be much larger than C. It can be much smaller than C, right? It can be anything. Then you look at the exponential graph ECG, where C is any constant, any positive integer, right? C. So ECG is the exponential graph of the graph G. Now the claim is that the direct product of G and ECG always admits a proper C coloring. That you don't need more than C colors to color this, right? You can always color the direct product with C colors. So why is this? So why is this? Well, the proof is just one line. Phi of u comma f is f of u is a proper coloring. Okay. So take the graph G and exponential graph ECG. Now in the direct product G cross ECG, what we have is that a vertex u of let's say G and a function or coloring f of ECG, right? That is the vertex of the direct product. So now the coloring of this vertex in the direct product of G and ECG is given to be f of u. So whatever is the function f and whatever is the vertex u, we know that f is a function which takes the vertices of G to some of the colors in 1 to C, right? So therefore, f of u is one of the colors from 1 to C. So if this is a coloring, then that is a C coloring because it uses at most C colors. So now phi of fu, phi of u comma f is f of u. The claim is that it is a proper C coloring. Of course, it is a C coloring we just saw. Now, why is it proper? Well, let us say that. Let me see if I can write it. Let us say that I have. It's visible, I hope. Okay. So phi of u comma f. Then I have, let's say, psi of let's say u v comma g. Okay. Now, if I have phi of uf and psi of vg, then when are they going to be adjacent, right? When they are going to be adjacent, well, the definition of adjacent in the exponential graph is that u must be adjacent to v, right? So this implies that if they are adjacent, if and only if u is adjacent to v, I think I should make it smaller. Yeah, u must be adjacent to v, and then f must be adjacent to g also, right? So u is adjacent to v and f is adjacent to g. If f is adjacent to g, if and only if for every adjacent pair of vertices, let's say u and v, f of u and g of v are different by the definition of adjacency in the exponential graph, right? So f of u must be different from g of v if u is adjacent to v, because f is adjacent to g in the exponential graph, right? So therefore, we know that this coloring is going to be a proper coloring. So that is the idea. Is it clear, or you want me to explain it more?
Clear, sir.
Is it okay?
Yes.
Okay, fine. Now, yeah. So now another observation is that the set of all constant maps, right, constant colorings form a clique in the exponential graph ECG. So why there is a clique in ECG? Well, because you look at the constant maps. So constant functions are the functions which give all the vertices of G the same color, right? So let us say that Gi is the constant map which takes all the vertices of G to the same color I. Okay, so it's an improper coloring if the graph is non-trivial, right? So then or non-empty, then you know that this is a constant coloring because all the vertices get the same color, right? Now suppose you have two such constant maps, let's say Gi and Gj, right? So Gi gives all the vertices the color I, and Gj gives all the vertices the color j. Now these two are adjacent in the exponential graph because by definition of exponential adjacency in the exponential graph, two functions are adjacent if they don't give the same color to adjacent vertices. Of course, the constant maps Gi and Gj always give I and j to vertices. So therefore, if I is different from j, then they are going to be different for any vertices, not just adjacent vertices, right? So therefore, the constant maps form a clique in the exponential graph. So how many such colorings are there? There are C such constant maps, right? So therefore, all of them form a clique of size C. So there is a C clique in the exponential graph ECG. So we know that the chromatic number of ECG is at least C, right? The exponential graph. Now, so this is again irrespective of what is the chromatic number of G, right? So I can always start with a graph G whose chromatic number is strictly greater than C. And then I know that the chromatic number of ECG is greater than or equal to C. Suppose I can show that the exponential graph has chromatic number strictly greater than C. Okay, not just greater than or equal to, but strictly greater than C. Then by the previous argument, we know that G cross ECG admits a proper C coloring, right? So G cross ECG admits a proper C coloring, but now we said that chromatic number of G is greater than C and chromatic number of ECG is also greater than C. Then we get a contradiction, right, to the heterodymy conjecture, because now we have a coloring with less than or equal to C colors, right? In fact, we have a C coloring of the product, as we said, and chromatic number of both of the components are going to be strictly greater than C. So that is a counter example to heterodymy conjecture. So that is our idea, right? We are going to prove that we can find a graph G whose chromatic number is greater than C and an exponential graph ECG that is also strictly greater than C. And once you prove these two things, we are done. Okay. Now, a fact that you can remember is that if two colorings have disjoint ranges, they are adjacent in the exponential graph. Okay? Because as we said, in the adjacency in the exponential graph is only if they give different colors to adjacent vertices. So if the two colorings, two maps have disjoint ranges, of course they are going to give different colors to adjacent vertices also, right? Not just adjacent, in fact every vertices they are going to give different colors. So therefore if colorings have disjoint ranges, or basically image of phi and image of psi are they don't intersect, then they are adjacent in the exponential graph. Okay. Yeah. So that is the claim. Image of f and image of g, if the intersection is empty, then f is adjacent to g in the exponential graph. So this is what we just stated. Yeah, so the idea of proof is the thing. If we have graph G with exponential graph also have chromatic number strictly greater than C, then we get a counter example. Right. So now we go back to the time of Paul Erdős, where he proved a very, very famous result. This was a very striking result. He proved that there are graphs with arbitrarily large girth and arbitrarily large chromatic number. Right? This is a well-known result of Paul Erdős. He showed that you can find graphs where the girth is the smallest cycle in the graph, right? Girth is the length of the smallest cycle, can be arbitrarily large, right? So there is no question about having a large click or anything, right? The click is going to be at most 2. So you can find a graph with arbitrarily large girth, and then still the chromatic number can be arbitrarily large. Okay. Now this result, when he actually proved something slightly stronger. Okay. So what he proved, in fact, was that there are graphs with arbitrarily large girth and arbitrary independence ratio. So alpha of G can be as small as possible, right? Dependence number, let's say, is so if P is the number of vertices in the graph G, then P by whatever number you want, you can make it. So alpha G can be smaller than P by whatever large number that you want. So we are going to take that number to be like 4.1 in this case. Okay? Whatever, something that works. Okay? So alpha of G is less than or equal to P by 4.1. So by Erdős result, we have graphs with girth at least 6 and chromatic number, the independence number less than or equal to P by 4.1. So the independence number is small, then the chromatic number will be large, because you know the result relation between the chromatic number and the independence number, right? So and the number of bits. So therefore we know that alpha of G is less than or equal to P by 4.1. There is such a graph G. Now so because of this result, we can take a graph with this kind of property. Okay, so yeah, so this is what we just said. So there are graphs with arbitrarily large girth and arbitrarily large chromatic. Now what we are going to do is that we are going to fix two parameters, P and Q. Q and C, where P we set to be the number of vertices in the graph G that we have obtained by using Erdős result. Okay. So we start with the graph G, whose girth is at least 6 and independence number at most p by 4.1, where p is the number of vertices. And then fix Q to be large enough such that it is larger than is greater than or equal to 2 raised to p minus 1 into p square, where p is the number of vertices in the graph G. Okay, remember that. So Q is some parameter which is very, very large, right, compared to p, right? 2 raised to p minus 1 into p square is much, much larger than p, right? Now, similarly, we fix C to be even larger. It's 4Q plus 2. Okay, so whatever is Q, 4Q plus 2 is C. And we already said that, you know, when we are looking at this exponential graph or anything, you know, we don't really worry about what is actually C, but you know, we can always look at all possible colorings using C colors, right? So we fix C to be this and Q to be this. Now the claim is that the chromatic number of G box KQ. Okay, what is G box KQ? Well, you have this graph G that we obtained, right? So you take any graph G that you want. Then every vertex of this graph G, I am going to replace with a copy of graph on KQ. Okay, so you have initially some graph G, right? Whatever it is, then every vertex I am going to replace with a copy of complete graph on Q vertices. Okay, so this vertex is replaced with a complete graph on Q vertices. Similarly, all these vertices. Now, then what I do is that whenever there is an edge, you know, so if there is an edge from, you know, this is, let's say, U and this is V, then the corresponding clicks I put a complete bipartite graph between them. Right? So I am going to make all of them adjacent to each other if there is an edge. If there is no edge, I don't do anything. Right? So here all I put complete bipartite graph like this. So corresponding clicks I put a complete bipartite graph. So I replace each vertex with a click on Q vertices. Right? So I'm going to increase the number of vertices of the new graph to be very, very large. So this is a G box KQ. Okay, so G box KQ is the not exponential, the graph obtained by replacing every vertex of G with a copy of KQ and putting you know, the corresponding edges by complete bipartite graph between. Now you take this graph GKQ and look at the exponential graph with respect to C. Okay, ECGKQ. Now the claim is that the chromatic number of both, right, GKQ and exponential graph ECGKQ are both greater than C. Now if we actually prove this claim, then we are done, right? We get a counterexample to the head-Nemes conjecture, because we already know that if you take the direct product, right, of G and ECG for whatever G is, right, it is always going to be C colorable, right? We proved that. Now, what we have here is that, you know, our G is now G box KQ, where G is replaced by KQ on vertex is replaced by KQ, and then, you know, that is our new G, and then similarly we apply the EC, you know, G KQ instead of, you know, the earlier G. So therefore, this result can be applied directly here. So if you know that both of them are strictly greater than C as a chromatic number, then the direct product of these two can be colored with C colors, which is a counterexample to head-Nemes conjecture, that, you know, it is actually equal to minimum, right? We get something strictly less than minimum. Okay, so is the graph GKQ clear? G box KQ.
Yes, sir. Yes, sir.
Okay. Well, as I tell you, any doubts, you please raise your hand or let me know. Fine.
Yes, sir. Sure, sir.
Okay. So, well, the first part of the claim is very easy to see, right? Because what happens when you replace the vertices, of the graph with a complete graph on KQ, right? So what happens is that the independence number does not change, right? Can you see that? Why the independence number does not change? Anyone? Anyone want to tell me why the independence number does not change for the graph G box KQ? So you start with the graph G, replace every vertex with KQ, put a complete bipartite graph between the corresponding vertices. Then the independence number of the graph does not change. I mean, the independence ratio does not change, right? Or even independence number, ratio changes, independence number does not change. So why is that? Okay, if there is nobody volunteering, I have to do it. Well, so we have the graph G box KQ, right? So G box KQ is obtained by replacing every vertex by a complete graph. So what is an independent set in the graph? Well, independent set is a subset of the vertices such that no two are adjacent to each other, right? Now, let us imagine the graph G had some independent set, right? Whatever the independent set you take. Now, if you pick one vertex from that, right? So because those vertices are already part here, right? We have just replaced with a copy of KQ. One of them will be present here. So if I pick any vertex from one of the copies of KQ, right? Then I cannot pick any other vertex from there because it is going to be a complete graph, right? And similarly, from each vertex, in the independence set corresponding to this thing in G, you cannot pick more than one, right? So is there any new independent set? Because we have only introduced clicks, there is not going to be new independent set. So therefore, what we can see is that the independence number cannot increase. And we can see that the independence number is at least as much as that was in the graph G, because we can still pick those corresponding vertices and there is no new adjacency created. So therefore, that is still an independence. And the independence number is going to be the same. Okay? So both G and G box KQ. Now, what does this mean? This means that the independence number of the graph was earlier, what was it? P by 4.1, right? Alpha of G. Now, what is that in the new graph? Well, it is still P by 4.1. So the chromatic number must be at least the number of vertices by the independence number. So that is a well-known result. So therefore, because every color class can contain at most the independence number of many vertices in the color class, right? Because color classes are independent sets. So therefore, the chromatic number must be the number of colors must be at least the number of vertices, which is P into Q, because I expanded every vertex of the graph G with Q vertices now, right? So therefore, it's P into Q, the new number of vertices, by the independence number, which is P by 4.1. Now, PQ by P by 4.1 is at least is equal to 4.1 into Q, and this 4.1 Q is greater than 4Q plus 2, right? Because Q is large. So 4.1 Q is greater than 4Q plus 2, but 4Q plus 2 is the number of colors C, right? By definition, C is equal to 4Q plus 2, right? So therefore, we know that chromatic number of the graph G box KQ is strictly greater than C. So we proved one of the claims, right? So all it remains to disprove the conjecture is to prove the second claim, namely chromatic number of ECGKQ is strictly greater than C. And that is what takes a little bit of work. So the remaining part of the entire talk is going to be to prove the second claim, which is chromatic number of ECGKQ is greater than C. So recall that we started with a graph G whose girth is at least 6, right? Number 1. And this result was obtained by Polar Dosh, right? So girth is at least 6 and independence number is at most the number of vertices P divided by 4.1, right? So we start with such a graph G, then replace every vertex of this graph with KQ, where Q is greater than or equal to 2 raised to P minus 1 into P square, right? Where P is the number of vertices in the graph G. And then we get the graph G box KQ, and we just proved that this has chromatic number strictly greater than C. And we are going to now consider the exponential graph of this ECGKQ and show that that also has chromatic number strictly greater than C. So recall these points when we go into the next pages. Okay. So the main claim is that chromatic number of ECGKQ is strictly greater than C. Now, so to prove that the chromatic number is strictly greater than C, we suppose to the contrary that there is a C coloring of the exponential graph, right? Right. So we want to get a contradiction. So to get that, we assume that suppose the chromatic number is equal to C or less than or equal to C, right? So we start with the assumption that there is a proper C coloring of the exponential graph ECGKQ. Now, we call such a coloring to be psi. Okay, so psi, capital psi, is a proper C coloring of ECGKQ. Now, without loss of generality, I can assume that this particular coloring psi gives every constant GI. Okay, so we already saw that the constant maps, that's GI, GJ, right? So all the constant maps in the function form a clique, right? This is something we proved, right? The constant maps form a clique in the exponential graph, right? Now let us look at the constant maps. Let's say GI. The claim is that any proper C coloring ECGKQ right must give different colors to the vertices of the constant colorings, right? GIs, because each of them are adjacent, right? They form a clique. The color that is given here, let's say C1, C2, and C3, right? They must all be different, right? Because they form a clique, and psi is a proper coloring. Now, if I have, and we know that the exponential graph contains a clique of psi C, right? Because there are C colors, and each of the constant maps, there are C of them, right? So each of them form a clique. There is going to be a C clique. So there is a C clique in the exponential graph, right? Now, if there is a C clique, then I cannot color with less than C colors, right? I definitely need C colors because all the C distinct vertices of the clique must get different colors. So I am going to use all the C colors. So now there is a C coloring of the clique. But now, if all the vertices are given different colors in this clique, so take any proper coloring, okay? So start with a proper coloring, and in which some vertices get red color and some vertices get blue color, some vertices get green color, etc. Now I can always rename the colors. Say that okay, all the blue vertices are now called green vertices, okay, and all the green vertices are now called blue vertices, right? This will not make the coloring improper, right? Because I'm just renaming the colors from blue to green and green to blue, right? So the same thing I can do, so that now because the C clique formed by the constant functions are all colored with different colors. I am going to rename and call that, okay, the coloring which is given to GI is now I rename it to be I, right? Wherever is I rename it to something else, right? Similarly, all the coloring for GJ, I am going to call it J, and GK, I am going to call it K. So therefore, now I know that there is a proper C coloring, right? If there is a proper coloring, then there is a proper coloring where the constant maps GI get the color I itself. Okay, so this is very important notion. Okay, this is one of the most interesting concepts that is going to be used many times in the proof. Okay, so so there is a recoloring such that the constant maps GI is mapped by the coloring psi to be to the color I itself. Okay, so psi of GI is equal to I. So GI itself is a constant function which takes every vertex of the graph G to the color I. Now psi is a map which takes the map GI to the color I. Okay, these are two colorings, right? One is the coloring of the graph G, one is the coloring of the exponential graph, right? Is it clear? Is it clear to everyone?
Yes, sir.
Yes, sir. Clear.
Okay. Now an easy observation is that this coloring psi has the following property. Psi of phi is in an element of image of phi, right? Image of phi is the range of phi, right? So psi of phi is an element of the image of phi for any map phi in ECGKQ. And this observation comes from the definition that we just said, that without loss of generality we can assume that psi of G is equal to I, right? This property gives you this observation. So why is that? Well, to see this, just look at a function phi. So for every phi, suppose I is not in image of phi. Okay, suppose I is not in image of phi, then phi is adjacent to Gi, right? Because phi is a map, and Gi is a map. Now, if the ranges are disjoint, we said that it's an earlier observation, said that two disjoint maps are going to be adjacent in the exponential graph, right? If the ranges are disjoint, then let me see if we can go to that observation. Yes, right? Im of f intersection Im of G is equal to MT implies f is adjacent to G in ECG, right? So we are using that result. Sorry. We are using that result to say that, yeah, so if I is adjacent to Gi, because I is not in the image of phi, and this says that psi of phi cannot be equal to I, because we know that psi is a proper coloring. So psi of Gi is already I, so therefore if phi is adjacent to Gi, psi of phi can be must be different from that of the color of Gi, which is I, right? So psi of phi is not equal to I. So this basically says that, you know, if anything which is not in the image of phi, I mean, like, that cannot be colored. So therefore psi of phi must be an element of image of phi. Okay. So fine. Yeah, so here is the proof. Em of phi intersection Em of Gi is empty, implies phi is adjacent to Gi, and psi of phi is different from psi of Gi since psi is a proper coloring. Yes. Now another important definition. This is that of a simple map. Okay. So we are looking at the maps or colorings of the graph G, right? A map phi, let's say, is simple if so we look at the you know, the graph. Look at the graph G box KQ, right? So G box KQ, every vertex of G is replaced with a copy of KQ. Now we are looking at the exponential graph of this graph, right? Now in this context, a map is simple if it gives the same color to all the vertices obtained by the expansion of a single vertex, right? So I have replaced the U with a copy of KQ. Now all the vertices in this KQ must be given the same color by any simple map. So that is the definition of simple map. Okay. So phi of U comma I is equal to phi of U comma J for I and J in Q, right? 1 to Q. So therefore, U1, U2, etc., UQ are all going to get the same color under the map phi. Right, so such maps are called simple maps. Of course, there are maps which are not simple, right? Because you can take this copy and give adjacent vertices different colors, of course, right? So so we have maps which are simple and which are not simple. In fact, we are going to look at most of the most of the maps that we are going to consider today in the later part is going to be simple maps, except one. We will mention that. So, so notion of simple map must be clear. Now, so every copy of vertex of G get the same color under simple maps. Okay, fine. Now, another observation is that if two maps phi and psi are both simple, then phi is adjacent to psi if and only if for every U adjacent to V, phi of U is different from psi of V. Right, this is by definition of adjacency in the exponential graph, and phi of U also different from psi of U. Now, why is this? Right? Now we know that if U and V are adjacent, phi of U must be different from psi of V by the definition of adjacency in the exponential graph. But why it must be the case that phi of U is different from psi of U also? Well, that is because of our construction of the GKQ, right? So GKQ, when I say a vertex U, it's basically a vertex U comma something, right? U1, U2, etc. So now phi of U and psi of U, right? So basically it's phi of U comma something I and psi of U comma something, let's say I or J. Now, since we know that whenever I is different from J, right, phi of UA is adjacent to UJ because it is a copy of a complete graph KQ, right? So we replace the vertex U by a copy of KQ. So therefore, even though they are distinct vertices, right, UI and UJ are basically adjacent in the graph GKQ, and therefore by the property of the exponential graph, they also must get different colors by the functions phi and psi if they are going to be adjacent, right? So UI is adjacent to UJ in the graph. Phi of UI must be phi of psi of UJ must be different, right? And this is because we use a simplified notation for the simple maps, right? Because when I say phi of U, it's basically phi of UJ. Okay. So and because all of the vertices UI and UJ are going to get the same color under simple maps, it doesn't matter whether I use UI or UJ. It's going to be just phi of U, because one vertex gets a color, all of them get the same color under simple maps. Right? So that is why we have this property. Okay. Now, another observation is that because of this observation, right? Phi of U not equal to psi of U, we can see that it's like having we started with a graph G where all the vertices had a loop on itself. Now, if there is a loop on itself, then of course a vertex is adjacent to itself, and if a vertex is adjacent to itself, then in the exponential map, the adjacent exponential graph, the adjacent functions must give different colors to the same vertex also, because U is adjacent to itself, right? Because whenever two vertices are adjacent, they must be given same different colors by the adjacent maps in the exponential graph. So even though we didn't start with such a graph, it is, after this, looking at the simple maps, one can see that the simple maps acts like, acts like we started with a graph ECGC0, right? G0 is the graph where I replace the graph G with a every vertex is introduced with a loop at each vertex, and this graph I take the exponential graph, right? ECG0. That is a subgraph of ECGKQ, right? Because that's what we just noticed, right? Because phi of u must be different from psi of u, right? So the simple map basically acts like we started with a graph with loops at each vertex. Now, yeah. So just to have some idea of the kind of graphs and the size of the graphs that we are looking at, right? For the counter example, let us note something. Okay. Now, if we wanted to have a graph with the girth at least 6 and the independence number less than the number of vertices by 4.1, right? Independence ratio small enough, then we need at least 200 vertices in the graph. Okay, this is something that you can verify manually. Okay? We can easily check that if the graph has girth at least 6, and then you want the chromatic number to be less than the number of vertices by 4.1, then it should have at least 200 vertices. Okay, so we start with a graph with 200 vertices, right? Then we define our Q and C, right? So Q is going to be 2 raised to p minus 1 into p square. So which is basically 2 raised to 200 minus 1 into 200 square, right? So this is going to be very, very large, right? And then we have Q to be for Q plus 2, C to be for Q plus 2. And therefore, one can see that now the graph that we are going to look at, ECGKQ, has C raised to PQ vertices, which is something like 2 raised to 200 whole raised to 2 raised to 200 whole raised to 2 raised to 200, which is like really, 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 really large, right? Really huge, graph. On the other hand, we are looking at this graph ECG0, let's say, right? ECG0 has something much smaller, right? Like 2 raised to 200 whole raised to 200, because it is only C raised to P vertices, right? Instead of C raised to PQ, right? We have only C raised to P vertices in the exponential graph. So the exponential graph has only this many vertices. Well, this is very, very large, right? I mean, more than the number of particles in the universe, right? Known universe and things like that, right? So that is the kind of graph that we are looking at this moment. Okay. Later we will, if we have time, we can see that like there are some recent developments where they have decreased the size of the graphs considerably. Yeah? Anyway, so at the moment we are looking at such huge graphs. Okay. Now, in the remaining part, we are going to concentrate on the following. So before that, let us just see what we have done so far. So we started with the graph G, and we said that we have graph with large enough girth and large enough chromatic number. So we started with such a graph with girth at least 6 and chromatic number at least p by 4.1, right? No, I mean like independence number at most p by 4.1, and then we what we did was that we defined your exponential, I mean not exponential graph, but the graph replace this graph G, replace every vertex with a copy of KQ, where Q is quite large, right? 2 raised to p minus 1 into p square. And then what we did was that for this graph we showed that the chromatic number is larger than C. And then we defined the exponential graph, right, of this graph. and then we are trying to prove that the exponential graph was chromatic number large also. So for that purpose, we define what is called simple maps, and which are maps which give the same color to the expanded copies of each vertex, right, in GKQ. Okay, so we are standing at this moment. Any doubts so far?
No, sir.
Okay, so if everybody is fine, we continue. Okay.
Okay, sir.
Yeah. So let us define I of VB as the set of all maps, set of all simple maps. So when I say phi is in ECG0, I am talking about simple maps, okay? Because we just notice that ECG0 is a subgraph of ECGKQ induced by simple maps, okay? So when I say phi is in ECG0, that is I'm talking about simple maps. Okay, so I of VB is a set of all simple maps with the following property, right? That the simple map phi takes the vertex V to B. Okay? Phi of V is equal to B. So B is a color, V is a vertex. In I of VB, V is some vertex and B is some color. So IVB is defined to be the set of all phi such that phi of V is equal to B, and then psi of phi is also equal to B. Okay. So the proper coloring psi takes phi to be, where phi takes V to be. Now we know that something like this is possible because we already observed that psi of phi is an element of Im of phi, right? So therefore, every VB, right, for every color B, there is some kind of some map which is going to take this property, because we know that psi of phi must be an element of phi, and now we know that phi of V is equal to B. Then there should be every such map should appear as one of these IVBs, right? It cannot escape any of this because of this observation that psi of phi is an Im of phi. So therefore, we can write the vertex set of ECG0 as a union over all possible V comma B, I of VB, right? So every coloring in the simple map must appear in one of the IVBs. So therefore, I can write the vertex set as union of V comma B, IVB. Now, let us see what is the size of IVB. Okay. So the average size of IVB is, of course, the total number of vertices is the total number of C colorings, which is C raised to P. Right? P is the number of vertices in G, and right, and C is the number of colors. So C raised to P, and the number of possible V comma P, right? So V, there are at most P vertices and at most C colors. So therefore, at most C into P possible IVBs are there. So therefore, average size of IVB is going to be C raised to P by C into P, right? Total number of colorings by total number of possibilities, right? IVBs. So that is the average size. Now I define IVB to be large if IVB is at least 2 into P into C raised to P minus 2. Okay. So if the cardinality is at least 2 into P into C raised to P minus 2, then I say IVB is large. Otherwise, it is small. Now, an important lemma is that there is some vertex V such that set of all B, right, set of all colors B such that IVB is large is greater than C by 2. So which means that for more than half the colors, for some vertex V, for more than half the colors, IVB is large. Okay. So how do we prove this? So for proving this, we define something we call S of V to be set of all colors such that IVB is small. Okay, so we said that IVB is large if IVB is greater than or equal to 2 into P into C raised to P minus 2. So therefore, if that is not the case, then IVB is small. So take all such vertices for which the set of all V is such that IVB is small, and you collect such sets and form a list out of this. Okay, so the list L is defined to be the set of all simple maps phi, such that for every vertex V, phi of V, right, the coloring of V under the map phi is an element of S of V, right? So that we only choose those guys which give small IVBs, right? Now I'm going to count this L in two different ways. Okay, so one is that the cardinality of L, I can talk it in terms of the vertices. So look at all the vertices. Each one has independently at most S of V, such small guys, and then you take the product of all these guys. So each of the one which is small must be at least C by 2, right? Because if not the case, then we know that there is some vertex whose IVB is large is strictly greater than C by 2. So therefore, each of them must be at least C by 2, so that we don't have this property of the lemma. And there are P such vertices, so therefore it is C by 2 whole raised to P. So L must be greater than or equal to C by 2 whole raised to P. So this is immediate if there is no such vertex V. On the other hand, we can also see L in another way, right? So I count L as the union over all V comma B, because we said that all colorings must appear as such a union. Now take IVB is small, cardinality of IVB, right? So what is the cardinality of L? That is the cardinality of union IVB, where over V comma B, where IVB is small. Now, if IVB is small, the cardinality of one IVB is at most C into 2P into C raised to P minus 2, and 2 into P into C raised to P minus 2, and the total number of possible is in the union is P into C, where P is the number of vertices and C is the number of colors. Now, from these two identities for L, we can immediately get that C is less than 2 raised to P plus 1 into C square. Okay, this is something you can just use this earlier inequality and this inequality. Both of them together will give C is less than this. But this contradicts, so this contradicts the choice of C, right? Because we already selected C to be 4Q plus 2, which is greater than 4Q. But 4Q is actually 4 into 2 raised to P minus 1 into P square. But here we are saying that C is less than 2 raised to P plus 1 into C square, right? So this is a contradiction. So that is what shows that there must be such a vertex V, right? There is some vertex V such that the set of all colors for which IVB is large is greater than C by 2. So more than half the colors IVB is large for some vertex V. So now we select this vertex and call it V star. Okay. So choose V star for which the lemma holds. So there is some vertex V star for which this is true. Now we are going to look at in the following, when we say V star, it is going to be this specific vertex. Is it okay? Can I continue?
Okay, sir.
Okay. So am I going late?
Sir, it is already 11:05, I think.
Yes.
How many more minutes would you require, sir?
I will need maybe 10 more minutes.
Oh, okay, sir. Then it's okay. No problem. Okay, sir. You can continue.
Okay. Because I think I mentioned it. If I want to go in detail, I need at least
No,
1 hour 20 minutes or
sir.
something.
No problem, sir. No problem.
Okay.
Sir. Okay, sir. Okay.
Okay. So now, so let us choose V star for which the lemma holds, and then we decide not we decide, we select some T, which is of course a color from the set 2q plus 1 to 4q plus 2. You know that the set of colors is 1 to C, and C is basically the set 1 to 4q plus 2, right? C is equal to 4q plus 2. So out of this, we choose the colors 2q plus 1 to 4q plus 2, which is more than half the colors, right? Okay. Yeah. So now, what we are going to do is that we are going to define some maps mu t as follows. Okay. So mu t of x comma I is defined to be the color I if the distance in the graph G between x and the vertex V star we just selected is either 0 or 2. Okay. If the distance is exactly equal to 1, right, then I give it the color q plus I, and if it is greater than or equal to 3, the distance, then I give it the color T itself. Now, of course, because we are talking about all possible colorings, such a coloring is also there, right? So we have such maps already present, right, in the exponential graph, because every possible coloring is there. So in particular, this kind of colorings are also there. Now mu t of xi is defined this way, and we can observe immediately that mu t's are not simple maps. Okay? Just look at and see what happens in the simple map in the GKQ. What happens when we give such colorings, whether this will satisfy this or not. Okay, this is something which you can easily verify. Okay, so mu t's are not simple maps. Now another claim is that the set of all such functions mu t's form a clique in the exponential graph ECGKQ. So mu t is are adjacent to each other for distinct t. So why is that? Well, suppose mu t is not adjacent to mu t dash, right? If they are not adjacent, then by the definition, there must be some adjacent pair of vertices in the graph GKQ x comma I and y comma j, right? Such that mu t gives xi the same color that mu t dash gives yj, right? So mu t of xi is equal to mu t dash of yj. But now, if they must give the same color, then let's say that these two colors to be equal to alpha, right? So this is alpha, right? Mu t of xi and mu t dash of yj is equal to alpha. Now alpha must be, of course, an element of the image of mu t, and it's also an element of image of mu t dash, right? Because they are in the intersection, because they are both getting the same color. Now, if alpha is in the intersection of these two, then in the first map mu t, it's only I q plus I or t, and in the second map it is j q plus j or t dash. Now, if I is t and t dash are different, of course, then what is the possibility for alpha? It is either I is equal to j, alpha is equal to I, or q plus I, right? Otherwise, this cannot be equal, right? Either I is equal to j and q plus I equal to q plus a. So I must be equal to j, and alpha is either I or q plus a. But now this says that xy is an edge of EG, right? Because we said that, right? If xi is adjacent to yj, x is adjacent to y, right? So if x is adjacent to y, then by the definition of mu t and mu t dash, right? If mu t is, if alpha is either I or q plus I, then we know that the distance from x to v can be at most 2, and the distance from v to y can be at most 2 by the definition of mu t, right? We define mu t to be, right? So it's either 0, 2 or 1, right? So it's at most 2, right? The other case doesn't arise. Now this says that xy is adjacent, x to v is at this is v star actually. X to v star is at most 2, y to v star is at most 2, which means that there is a cycle of length 5 in the graph G. But we assume that we started with a graph whose girth is at most girth is at least 6. So this is a contradiction. So therefore, mu t must form a clique. Okay. So as a consequence, we have some t star. The psi of mu t star is equal to t star because we have a clique with more than half the number of colors, and therefore, and this set has strictly more than 2q 2q plus 1 colors, and therefore if you look at the definition of mu t, it's going to be either I or q plus I or t. Now I and q plus I can have range at most 1 to 2q. It cannot be more than 2q. So the set of such colors is at most 2q, and we have at least 2q plus 2 colors in this set. So therefore, at least one of them, it must be the case that it is going to get not I or q plus I, it must be equal to t. Now if that happens, the only possibility is that t star mu t star is equal to t star, right? Mu t is equal to t. Okay. Now the claim is that there is some b star, right? Some color b star in the set 1 to 2q comma t star. So the t star is something that we choose just now. There is some t star mu t star for which psi of mu t star is equal to t star, right? So therefore, now we select such a mu t star and say that okay, 1 to 2q comma t star is a set with at least c by 2, and since I of b star is large, define theta belonging to ECG0 as theta of x is equal to b star if distance in G of v star comma x is greater than or equal to 2, and it's equal to t star if distance is at most 1. Okay. Now the claim is that and theta is a simple man. Okay, this also you can check. Now claim is that theta is adjacent to mu t star. Because of lack of time and the similarity of the proof that we proved in the previous thing about the adjacency, we can just show this claim by looking at theta not adjacent to mu t star. What happens? Again, get a contradiction for the length of the smaller cycle. Okay, from this. So just follow these arguments. So I will not go into details, but it is the same proof, very similar to what we did before. So therefore, we can find such a b star. No, theta must be adjacent to mu t. Okay, so now they are adjacent, being a proper coloring, psi has to give different colors to theta and mu t star. So psi of theta is different from psi of mu t star, but we know that psi of theta must be either one of the ranges, because psi of anything is and in the image of the function, right? So Im of theta is either b star or t star. Now, if it is not equal to t star, then it must be equal to b star. So we know that psi of theta is equal to b star. So that is a conclusion that we can get from this. Right? Fine. Yeah. So now the lemma says that for every phi in I v star b star, you can find a vertex x different from b star such that phi of x is in b star comma t star. So our idea of the proof is to to count I v star b star in a particular way and show that the assumption that I v star b star is large is some there's a problem, right? So it leads to a problem, and that is how we prove that the coloring psi cannot be proper. Okay? So for that we are going to restrict the choices for certain colors, and then for that we already said that for every thing phi of V star is equal to B star, that the V star has only one choice. Now we are saying that there is some other vertex who has only two choices. Okay, so there is some vertex x such that phi of x is an element of B star comma T star. Now again the proof is very similar to what we did earlier. By assuming adjacency of x and y, we can show using the distances. So again, the girth is very important, right? We started with this result of Herdosh, where the girth is at least 6, and if we assume that, then we can again show that there is a contradiction. So just go through this argument here. Because of lack of time, I am just skipping it. But one can quite easily show that there is some map. For every map, there is some vertex different from B star, which has only two choices, either B star or T star. Okay. Now finally, so this is the last slide. So we already have the following, that we have a vertex different from B star, whose image is either under phi is either of the two colors B star or T star, right? Now for every x different from B star, define Jx to be the set of all simple maps in I V star B star such that phi of x is in B star or T star. Okay, so collect all such maps for each x. Okay, so for every x we define this. Now what we do is that by the previous lemma, we know that for every map phi, it is in some Jx, right? Because we said that yeah, every map phi belongs to I V star B star. There is some x such that phi of x is in B star T star. So using that lemma, we know that some x must contain this phi. So every phi must be appearing in this way. So therefore you can use union bound. I of V star B star is equal to union over all x belongs to Bg minus V star, because V star we have kept aside, Jx. Okay, because each of the phi must appear one of these ways, this union contains all of this. Okay, so this union contains every such element in I V star B star. Now let us look at the cardinality of Jx. So cardinality of Jx is almost, well, V star has only one choice, and the selected element Jx, x has only two choices, right? Two colors possible. Every other vertex can have any of the, let's say, remaining colors. Let's say, I mean, any of the remaining p minus 2 vertices can have any of the colors. So therefore, Jx is at most 1 into 2 into c raised to p minus 2. Now, what does this say? This says that cardinality of I V star B star is less than or equal to, in the union, there is x belongs to Vg, right? Vg minus V star, right? So there is p minus 1 choices for x. So 2 into c raised to p minus 2 into p minus 1. That is the total number of possibilities in I V star B star. But I V star B star is now less than or equal to 2 into p minus 1 into c raised to p minus 2. But we already started with the assumption that I V star B star is large. So this is a contradiction. And this contradiction is because we assume that the coloring psi is proper. Because there is nothing else we assumed, right? Everything else was from the basic concepts only, right? So there is yeah, that is the proof, right? So we proved that I of V star B star is large, leads to a contradiction, and therefore our assumption, the only assumption that we made was that the coloring psi was a proper C coloring, and that is wrong. So this proves that there is no C coloring of the exponential graph ECGKQ. We already proved that the product is C colorable, so therefore this leads to a counterexample to heterogeneous conjecture. So I stop here, and there are some later developments showing that there are graphs with small enough chromatic number. In fact, even this has been improved to like something like 15 or 14 or something. Okay, 225. So we will not visit that. So thank you, and I hope that you have followed at least a major part of the talk. Welcome.
Thank you, sir. Now the participants can ask their doubts. I think there is a question in the chat box.
Okay, I didn't see the chat because I was in the presentation screen. Okay, let me see.
Yes.
Okay.
So what was the chat? Let us see. Applications of graph theory navigation. Ayyo, I have no idea. Okay. Of course there are applications because for example Google Maps and things like that are basically looking at this as graphs with nodes and all, and then the paths are edges kind of thing. But I am not really prepared to answer like how this is implemented or anything. These kind of things I have not looked at much. I mean, I know that these things are there, but there are several things. So I am more of a theoretician, like I work mostly on theory. If specifically asked, like I can prepare and talk about these things, but at the moment, offhand, I can't really know what exactly are the algorithms used in this thing. And of course, the graph traversal algorithms are always there, but which specific ones they are using for this optimization, I don't really know at the moment.
There is another question.
Yeah, suggest a good topic in graph theory for an undergraduate student. Well, so many topics in graph theory are good for undergraduate students. In fact, every topic is okay. And as far as you don't go to like something very difficult that you cannot understand. But most of the things should be possible. Like I had many students doing BTech students who used to take up even research questions. So, coloring is something that I have worked on a lot and something which people can understand easily. Graph coloring. Then there is also things like linear algebra, applications of in combinatorics and graph theory. So that kind of things must be like you can see the connection between two different areas, how they interplay and all. Like there is a good book written by what is his name? Frankel, not Peter Frankel, and one more Babai and Frankel. Yeah. So Laszlo Babai and Peter Frankel has written a book on this. So this is not just graph theory; it's both combinatorics and graph theory. You can see several applications of linear algebra there, and it's a very interesting subject. Then you can look at algorithms, graph algorithms. Again, undergraduate students can look at so many questions on algorithms. So yes, tell me. Anjali, you were saying something?
No, sir. Sorry, sir.
Okay, sorry. Yeah. So these are all good topics. Coloring is something which every student can. Even like things like very advanced topics like minor theory and all will be very interesting with lots of questions. But so basically you need to read in a lot of material. If you are willing to spend time on that, even graph minor theory, at least the basic parts of this one can look at, and then if you find some interesting, there are so many questions there which is unanswered and interesting to look at. So yeah, each of this coloring has so many variations. Minor theory has huge applications. And then probabilistic arguments, if you are like probability, like the coloring and even other structural arguments can have probabilistic analogs, which helps a lot in proving existential results. Each of this, yeah, I mean, there are very good books. If somebody wants, you can just send an email to me. I can suggest good books to read, at least what to read and all I can suggest. But more than that, I don't really know. And I used to work on graph coloring for many years. Recently, I have switched to, or at least partially switched to more structural graph theory and applications of combinatorics into commutative algebra. So this is, so that kind of work together with one of my colleagues. So, but that may not be very apt for undergraduate students, because I don't think people know enough commutative algebra to really look at these things. Okay, so that I wouldn't suggest. But coloring, graph algorithms, and graph minor theory, and structural aspects, all these are good for undergraduate students. Okay, anything else?
So just the book to start with this graph theory for beginners.
What is the book to start with graph theory? Well, one of the good books is like most famous is, I mean, there are many actually, many good books. One you can always have lots of examples, exercises is by Douglas West, Introduction to Graph Theory. Okay, so I can write Douglas West. So Introduction to Graph Theory. It's a very good book because it has so many exercises and examples. So if you are really interested and hardworking, then this will help a lot. Then there is Graphs and Digraphs by what are the names? Goetzel and Zhang, I think. There are three others. I forgot. Lesniak, yeah. So Lesniak. If you look for graphs and digraphs, Lesniak, graphs and digraphs. This is also a very good book. Little more advanced, but it also covers a lot more things. Then even more advanced book, but very interesting short book is by not very short now, I think, by Diestel Graph Theory, Reinhard Diestel. So all these three books are very good, okay, for graph theories. Douglas West. So Douglas West is something any student can look at and easily read and follow. Diestel, they need to understand a little more of things to follow some parts at least. Lesniak is easy enough to follow, but probably not as rich on Douglas West as its exercises. Some exercises can be much more challenging, but it's also good.
Thank you, sir.
Okay.
Is there any doubt for other participants?
Yeah. So this talk, I mean, like not this talk. This proof is actually, it's not very complicated. If you work out the details, go through it. Each step is kind of easy to follow. But it took 50 years, to find out such a proof is itself saying, things are not as easy looking in graph theory as people imagine. And this is one of the reasons, like one of the problems that in India, people jump into graph theory, start doing things, and then they find that they cannot really do anything. Then they end up doing something completely, nonsense. Lots of results are like, completely, on the surface, useless and all. So, like it's quite terrible situation in South India. Like, so many people working graph theory, but they don't look at the challenging questions, because they are kind of afraid to jump into that, and then they look at things, and then it has given a bad name to graph theories. So but I think there are so many questions to look and answer. What people should do is to look at challenging questions, and then if you take a very good challenging question, even small results progress on that can be appreciated. And writing proofs, again, I have found to be kind of very lousy by many people. So let us hope that these kind of things will improve soon. And yeah, so reading the proofs from these books, and studying this in detail will be a good exercise for students to appreciate how to write proofs and things like that. And you have to ask them to read it rather than just teach them. Like if you teach everything, they will not learn anything. Okay, you have to give some gaps and then let them work out. Okay? So that is the idea. Okay. Anyway.
Thank you, sir. Sir, could you please stay back for a few minutes, sir? We will be having a very short valedictory session because it is the last day of our webinar series.
Okay. Sure. No problem.
Yeah. Okay, sir. Thank you. Arya.
So I welcome the HOD of Vimala College, Thrissur, Swarnamis, for rendering her felicitation.
Thank you, Arya. Good morning, everybody. At the outset, I thank all the resource persons and participants for making this webinar series a success. Now I can say it is a success because we are at the concluding session of this webinar series. First of all, I congratulate Dr. Anjali Kishore, the Department Coordinator of DBT Star College Scheme, for taking initiative, selecting topics, and inviting resource persons, which is the most important part of this webinar series. I also take this opportunity to congratulate all the committee members, especially the technical committee and feedback committee, for doing their duty in a perfect manner. Our student representatives, Anne Christine Benny and Arya Prasad, also deserve appreciation for comparing these sessions. We are glad to have participants from Morocco and also from all over India. Actually, we started the webinar series as a national webinar series, but it became international. All these participants are connected by one language, the language of mathematics. I wholeheartedly wish that this relationship should continue. All of us should be connected for bringing out new results in different areas of mathematics. My speech will be incomplete if I don't mention the names of our principal, Dr. Sister Veena Jose, and DBT Star College Coordinator, Dr. Sylvie Matthew, for their continuous support and encouragement. With these words, I wind up. Thank you all.
Thank you, Swarnamis. Now we wish to hear the feedback of our webinar series, which just started from 2nd December from the participants. So participants can say their feedback about our webinar series.
Yes, they can unmute. They can switch on their video so that we can see the participants, and you can say something about this webinar. Your suggestions are welcome.
Hello, ma'am. Hello, can you hear me? Hello?
Yes, we can hear you.
Yes.
Yeah. So a warm morning to one and all. I'm Karthika from S6 BSc Mathematics, Vimala College. As it is customary to do our final year project, we were really confused about what topic to stick on and which all areas would help us in guiding a very good project. So these webinar sections helped us a lot in this. And we are really privileged to hear the classes of renowned professors from prestigious institutions. And all the topics discussed were new to us, and it gave us a very good basic information. And it also inspired us to go for future research. So I would like to thank our HOD, Swarna ma'am, Anjali miss, and all our teachers for this wonderful session. Thank you so much.
Thank you, Anka.
Thank Anyone else?
Hello, ma'am.
Anyone else would like to? Yeah, Aditya, come on.
Yes, I'm Aditya from Mathematics Department, Vimala College.
Aditya, we can't see you.
Ma'am, I'm not able to on the video.
Okay. Then, okay, continue.
Okay. First of all, I'm thanking all the coordinators for organizing such a wonderful webinar series. It helped us a lot to enrich our knowledge. It gives us an opportunity to interact with famous personalities from esteemed institutions. And it helped us to know the wider applications of mathematics in various fields, and it created enthusiasms in our subject. And in general, it underlined the fact that everything around you is mathematics, and mathematics is in everything. Thank you, ma'am, for organizing such a wonderful event. Thank you.
Thank you, Aditya.
So, is there anyone else? I think we can. There is no more else, I think.
Okay, so
Yes,
Jagdish, yeah.
Ma'am, this is Jagdishan from Tamil Nadu.
Yes.
Thank you very much for your DBT sponsor this seminar. Actually, for not only for beginners, from the beginning itself to the advanced level, each resource person explained like this way, from the beginning to the advanced level. So all the sessions were very informative sessions. So thanks for the organizing committee to make this seminar in a successful manner. Thank you so much for everyone, ma'am. Thank you.
Thank you, Jagdish. Thank you.
Thank you, ma'am.
Yes, now I think we are almost at 11:45.
Yeah, thank you all. Now I invite Dr. Anjali Kishore for the vote of thanks.
Yes. So actually, I had written a 4 to 5 page vote of thanks, but I think whatever I have written, Swarna Miss has already told everything. So I am in a position what to say. But because it is a formal vote of thanks, I have to say it, especially to today's resource person. So I would start with respected principal, Dr. Sister Beena Jose, honorable resource person of the day, Dr. Narayanan sir, Dr. Sister Sylvie Matthew, the Star College Scheme Coordinator of Vimla, my dear colleagues, participants from outside, including faculty, research scholars, and my dear young emerging mathematicians. A very good morning to all of you. First and foremost, I bow my head before God Almighty for blessing us with all that we needed to make this webinar happen. Now I take this opportunity to thank all our resource persons, beginning from Professor Parameswaran Shankaran, Dr. Sudarshan Iyengar, Dr. Yayadi, Professor Sunita, who is my own research guide, Dr. Sunil Matthew, Dr. Hari Verma, and Dr. Narayanan, who is today's resource person who is with us, for their support and cooperation, for being ready with such wonderful sessions amidst this pandemic period, and in spite of their personal and professional schedules and difficulties. So from the bottom of our heart, we, the Department of Mathematics, Vimla College, express our deepest sense of gratitude to each one of you, especially to Narayanan sir. Our principal always had been our constant source of inspiration and guidance. Sister, in your absence, we would like to express our sincere gratitude for all your support. Dr. Sylvie Matthew deserves a special word of appreciation and gratitude because she is there for all the ventures of DBT Star College scheme. Appreciation should be there for my dear colleagues. It was our teamwork which made this dream of ours a reality. So thank you all my colleagues, Swarna ma'am, who is always there with her strong support, Jinsi, Dolly Miss, who was the technical support for us, then Akita, Divya, and Fiji for all your support. The technical support rendered by Vishnu and Albin has made this event carry out smoothly. There were no much technical glitches so far that we experienced during our webinar session. Now, a special note to my students and Christine and Arya and all my PhD scholars for their help and support. Anne was there from the beginning when we started with the work of brochure. She was there, and Arya was there for comparing, and all my PhD scholars were there for giving the welcome speech, for giving the vote of thanks for various sessions. So thank you all once again. And last but not the least, all the participants, we express our sincere gratitude for all your wholehearted support and participation. We expect the same support from all of you for our future endeavors too. So thank you all once again. Thank you. So thank you, sir, once again for your wonderful class, sir. I know for an undergraduate student, it may be a bit difficult to understand what he has said, but surely I know that they have got some glimpse of it, and they will surely search for further and further studies in this area, sir. Thank you so much, sir.
Let me hope so. Yeah, because I mean, I think that this is something which they can actually follow. I mean, if they spend some time to work out the details.
Yes, sir. Yes, sir. Surely, I think
through the slides or some in the lecture again, and then work out the details if they are interested. And this is one of the most important results in the recent time, right, in graph theory. So,
yes, sir. Yes, sir. Yes, sir. Of course.
So that's why I decided maybe
yes,
they can look at something like this. So anyway.
Yes, sir.
Okay, thank you.
So thank you once again, sir. Thank you. Yes,
invitation and.
Thank you, sir. Thank you very much.
Okay.
Thank you, sir.
Okay, so
now, yes, sir. A word for the participants. There will be an overall feedback given in your group, and please fill the overall feedback. Then only you will be able to get the certificate. That will be put today or tomorrow, Surna ma'am?
Yeah, we'll put it today.
Okay. Yes.
Okay, so the overall feedback will be shared in the WhatsApp group.
Yes.
Okay.
Okay, so thank you.
Thank you.
Thank you very much.